this is worth your time to go and check. Let me check this. It hinges on the fact that the square of the sine of an angle plus the cosine squared of the same angle is equal to 1. This is a unit circle identity. And it turns out that this phi could be time dependent, but as long as they have the same time dependence, this will always be 1. The squares, right? You don't see any squares in the v of t, but when you take v dot v, so v squared, these get squared up, and that's where the time dependence goes away because of this unit circle thing. Okay, so we're continuing to be physicists. We've got this incoming momentum, impulse happens to it, outgoing momentum. The impulse momentum theorem what it says is delta P is equal to the impulse by the net force. That's what this means. We went through some steps to calculate the impulse delivered during between two times, t1 to t2. So I know how to calculate J net. It's here. Here are the two parts of it, the x part and the y part. The impulse and momentum theorem tells us that what these two things are, when you combine them up in a vector, they are delta p. They are the difference between p later and p earlier. Here's p later and there's p earlier, and this is the impulse that went into causing the change, or is associated with the change, or is the reason for the change. Yeah. Okay, so I'm going to rewrite this though. I think that what happens next, we're just being physicists. We're drawing pictures, thinking about how different physicsy quantities change, or why they change, which way they will change into. This has got to become that. And here is a theorem that describes why that change occurs, or why these two things have the difference that they have. Okay, so yeah, we're being physicist right now. Not a lot of flashy math. The flashy math is fun, but this is the physics part. You might say this is the flashy physics part, the impulse momentum flash. Okay, so I like to take this formula and rewrite it into a different way. Delta P and J net are the same thing according to this theorem. So I'm going to say that P2 is equal to P1 plus a change. And this change is vector valued, and the change is what is the meaning of J net, right? So P2 is P1 plus J net. P2 is here, P1 is here, and J net is the difference between the two. So P2 is here. It is equal to P1 there plus a vector called J net. All right. So let's look at this. This is a vector equation. It was a vector equation here and here as well, honestly, but this is where it's explicitly a couple of arrows. The arrow P2 points purely leftward and has this magnitude. The vector P1 has the same magnitude, right, because the momentum magnitude doesn't change in this uniform circular motion. It's got the same magnitude, but it points upwards instead. And J net is the vector. If I add it to P1, I'll get P2. So check this out. If this is P1, the vector that I need to add to it is this one. Because P1 plus J net equals P2, where P2 is the arrow that sits right here. So we're continuing to be physicists. We're thinking in terms of, honestly, like long and short arrows. Turns out that that's a nice way to encapsulate the physics of the impulse and momentum theorem. Impulse and momentum are centrally, they are vector issues. So when you think in terms of impulse and momentum, you must think about vectors adding and subtracting. These are vector equations. This is very different from the conservation of energy or the work energy theorem. Those are numbers. Those are scalars. Energy is a scalar problem. Momentum, though, is kind of like three different scalar problems. An x scalar problem, a y scalar problem, and a z scalar problem, where the x, y, and z are separate, independent problems. But the summary of that is arrows. The summary of the multidimensional scalar problem of momentum impulse is to do vector stuff, where the various directions are at right angles to each other. They're independent issues. Another way to view what's going on here, so another way to view this, J net must remove all the y direction momentum and replace it with negative I hat direction momentum. So you could think of J net as the thing that fixes the earlier vector, or the earlier momentum, the initial momentum. It fixes it into the new momentum. And it does so by removing everything that's wrong and adding back into everything that's correct. That's a weird way to view it, but that is what J net does. It removes everything that doesn't need to be there anymore and adds all the stuff that does need to be there afterwards. So in particular, we had P1, the incoming momentum, being purely upwards, but the outgoing momentum is purely leftwards. So we've got to, so since we have no vertical momentum here, no vertical left, and this has no horizontal at all, J net is the vector that's going to take something that has no horizontalness and make it into something that has no vertical left but does have horizontal, right? So this adds horizontal and subtracts vertical, or removes. You could say like removes. This is another way to view what the impulse momentum theorem does. So P2 equals P1 plus this J net. So it's P1 plus, so this is when it gets interesting. The integral from, or between two times, of the time-dependent net force multiplying small time intervals, dt. So if this is a summation instruction, right? That's what an integral does. And these things right here are small vectors, if you think about it, we are saying that our final momentum is equal to our initial momentum plus an infinite sum of really small vectors called dj. So I want to imagine thinking about these really small vectors. So these small vectors are f net at different times times a small time interval, and f net at the different times are these f centripetal. So early on it points towards the left. Whoops. So this little vector dj is a leftward pointed vector. And then a little bit later in time it points a little bit down to the left, more down, less to the left, even more downwards and even less to the left. And at some point it becomes purely downwards. So this little thing is a bunch of little tiny vectors adding up towards the, that way. So with that in mind, continuing to, think like a physicist, let's write P2 equals P1 plus the integral T1 to T2 of these little dj vectors. They are small amounts of impulse delivered by the net force, like this. P2, it's the momentum upon exiting the circular roadway. This is the moment in time that we have that momentum. That momentum is the leftward momentum. So this is a leftward arrow whose magnitude is m omega r. That's P2. It's equal to P1. Our incoming momentum was a purely upwards arrow, also with the magnitude m omega r. And then plus, what I'm saying is, here we must have to add up a whole bunch of little tiny small vectors. But those small little tiny vectors start at T1, they start leftward, and then as I go across time, they end up downwards. And we have to add all of those things up. So what that looks like is it starts off with a small vector leftwards, and then another small vector a little bit down to the left, and another small vector a little bit more down, less left, even more down and even less left, almost completely vertical, and now finally vertical. But really, it's an infinite number of them, right? Just, yeah, infinitesimally long, but an infinite number of them. That's the calculus limit. So what I'd like to show you is if I take this vector and then add all of these little vectors to it, I'm going to end up with this last vector. So I take this starting vector and I add to it the first vector, goes like this, and then I add to this plus this, I add that one, right? So in between all of these is a plus. So it's just this long string of pluses, starts with a big one and then adds on a whole bunch of small ones that are small incremental corrections. So you can probably guess how this plays out. So if I add P1 plus all of the small dj's throughout the time, I end up with P2.